Hi, everyone. Welcome to Chapter 4. Chapter 4 is going to be about covalent compounds. We started talking about those back in Chapter 3. I started off that chapter by pointing out that while ionic compounds form when you have a metal or ammonium, NH4, if there isn't a metal and there isn't an ammonium, you're going to be forming covalent compounds, or molecules that will have covalent bonds. So that's what we're going to go over now. And this is the handout that is posted on Moodle that you can fill in as we go through this presentation, or do it later on your own as you go through the PowerPoint again. And here we go. Chapter 4. And I'm going to press this button down here and make it nice and big. So here we go. Covalent compounds. We're going to use the periodic table to help us with this. I need you to remember that covalent bonds are formed when two nonmetals combine, or when a metalloid bonds to a nonmetal. Essentially, if you are not a metal and you form bonds, you're going to be with other not metals, you are going to make covalent bonds. Why don't nonmetals form ionic bonds with each other? Unlike metals, nonmetals don't easily lose electrons. The bullies, or the nonmetal elements, they aren't strong enough to take an electron away from an atom that is just a few electrons away from being like their nearest noble gas. Unlike the metals that want to lose electrons, and the nonmetals that are nearby are like, woohoo, we're going to take those electrons, we want them. If it's only nonmetals around, or only nonmetals and metalloids around, nobody wants to lose their electrons. Instead, they have to learn to share. So they had to head over to kindergarten and spend some more time sharing over there. All right. So even though our nonmetals and metalloids won't be taking electrons away from metals, those nonmetal and metalloid atoms still have the goal of having the same number of electrons as their nearest noble gas. When we focus on the valence electrons that the noble gases have, we will see that hydrogen, whose atomic number 1, he has 1 electron to start with. He's going to want a total of 2 valence electrons, like helium. Helium's the noble gas, so all the way in the right-hand column of the periodic table, helium's atomic number is 2. He has 2 valence electrons. That's going to be hydrogen's goal. How does he get there? Well, if he's with a metal, he's going to take 1 electron away. Then he gets to go to the cool parties with the noble gases. If he's with nonmetals or metalloids, then he's going to share an electron. The other nonmetals and metalloids will want 8 valence electrons, so they can be like neon, argon, krypton, or xenon. Those are the noble gases in group 8A. That set of 8 valence electrons that matches the group number for the noble gases, 8A, that is known as an octet of an electrons. So you may see something when you're looking in other materials or in your book, they'll talk about having an octet of valence electrons. Elements want to get an octet of electrons in their valence shell, that outermost shell of their atoms, the ones farthest from the nucleus. Let's watch an animation of covalent and ionic bonds. And to do that, I'm probably going to need to set it up so that we'll have some sound. So I'm going to pause this for a second, and when I come back, we'll look at it.
The outer shell of many atoms, hydrogen being an exception, holds 8 electrons. Atoms that have an outer shell containing 8 electrons are considered chemically stable. We often say they fulfill what is called the octet rule. When atoms combine to form compounds, they can give up, accept, or share electrons in order to assemble an octet of electrons in their outer shells. A covalent bond is formed when atoms share electrons in order to satisfy the octet rule. For example, a carbon atom holds 4 electrons in its outer shell, but it would be much more stable with 8. To gain the additional 4 electrons, carbon can share with other atoms and thereby have a completed outer shell. If 1 carbon and 4 hydrogen atoms come together and share their electrons, carbon achieves an octet of electrons. Note that each hydrogen in this compound achieves 2 electrons in its outer shell. This is the stable configuration of the first electron shell. An ionic bond forms when 2 atoms are held together by the attraction between opposite charges. The reaction between sodium and chlorine atoms is an example of how an ionic bond is formed. Since sodium has only 1 electron in its third shell, it has a tendency to give up that electron. Once it does, the remaining outer shell contains 8 electrons. This loss of an electron gives sodium a slightly positive charge. Chlorine, on the other hand, tends to gain an electron, since its outer shell already has 7. When chlorine gains an electron, it becomes slightly negative. The charged sodium and chlorine atoms are called ions. Ions of opposite charge attract each other and form ionic bonds. In this case, the attraction of sodium and chlorine form a molecule called sodium chloride, or table salt.
Okay, I hope that was beneficial for you. A little bit of review of ionic compounds, and then talking about the covalent compounds and the sharing of electrons that lets them feel, at least part of the time, that they have the same number of valence electrons as the noble gases. With the nonmetals and the metalloids, it's going to be the noble gases that are in the same row of the periodic table. Remember, when you're gaining electrons, even if it's sharing, so you have part-time custody, even then you are going to be going forward towards the noble gas in the same row. We can draw the symbols with the different elements, showing a dot to represent the valence electrons. So here I'm looking at the symbol for hydrogen, which is a capital H, and then beside each one there's 1 dot. That represents the 1 valence electron that those hydrogen atoms have. Now they want to share electrons with each other so that they have at least temporary custody of 2 electrons at a time. Those 2 valence electrons will make them be like helium. By himself, hydrogen has only 1 valence electron. If he shares that electron, however, another atom will share one of their electrons with him. This way, at least some of the time, hydrogen can have the same number of valence electrons as helium, his nearest noble gas, the one that's in the same row as him, but is in group 8A. This makes the hydrogen atoms more stable. Atoms will gain, lose, or share electrons to become more stable. And they're most stable when they're like their nearest noble gas. And that's in terms of electrons. It's hard when we're talking about these atoms that, this dot here, that's a pretty big one. That's bigger than what I would have on my paper. In that dot, there's probably about 100 million electrons in that one little dot. So it's tough for us to talk about these numbers and to show these things moving around in a way. It's not like a lot of biology and stuff. I can see chromosomes and things through a microscope, but we can't do that on this scale. So here's an animation that I like. that goes through and shows how electrons move in compounds with using little dots to represent the electrons. And let's see, it should start up pretty quickly, but I'll pause and come back to it in a second. Okay, let's take a look at this one.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has one valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with one valence electron needs one additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons.
Notice how hydrogen right now is about to have 2 valence electrons around him, just for a moment, but for a second there he'll have 2. Then oxygen will be back down to a 6, but in a second right after that, he's going to have all 8 around him. And in fact, later in this chapter, we're going to learn that the electrons will hang out around oxygen's nucleus longer than they will around hydrogen's nucleus. And I misspoke. I forgot right now we only have one hydrogen atom. So that hydrogen atom will share his electron with the oxygen, who will go from having 6 valence electrons to 7. He's not going to be stable yet. He doesn't have his octet yet. So we'll see in a moment. So he needs help from another hydrogen. Again, there'll be a brief moment now where the oxygen has 2 valence electrons around him. One that he started with, the one he came to the party with, and then temporarily he'll also have one that's being shared by oxygen.
By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still one short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
Okay. So hopefully that was helpful for you, and I'll be right back. I want you to notice how in the video we saw, they were showing the shared electrons as the 2 dots. Notice how that becomes a straight line in our final drawing. So while we start out with 2 dots to represent the electrons, our final drawing just has a straight line. That represents the 2 electrons that are being shared in this covalent bond. Now we have a little bit of a new twist. We've been talking so far about compounds. We had our atoms, we had our ions, which were charged atoms, and then we had ionic compounds. We have a new word to add in now, it's molecules. We use the term molecule if we're talking about a unit that has only covalent bonds. There is no such thing as an ionic molecule, but we can talk about covalent molecules and covalent compounds. H2, where we have the 2 hydrogen atoms that are covalently bonded, that are each sharing an electron with the other atom, That's known as a molecule of hydrogen, because the hydrogen atoms are connected with a covalent bond. H2 is also an example of a diatomic molecule because it is made up of only 2 atoms. HF, hydrogen fluoride, is also a diatomic molecule. There are 7 elements that exist in nature as diatomic molecules. This is very important. There are 7 elements that exist in nature as diatomic molecules. So the air I'm breathing in right now, when I say I'm breathing in hydrogen, it's H2. Most of the air that we breathe in, about 76% of it, is nitrogen gas. Nitrogen atoms don't exist by themselves. Remember, they're not stable that way, but they exist as a pair of nitrogen atoms that share valence electrons with each other. That makes it a diatomic molecule of nitrogen. It's still considered an element. It's just always going to be 2 atoms together. The oxygen I'm breathing in right now, it's not individual oxygen atoms. It's 2 oxygen atoms bonded together covalently. Now, I don't want to breathe in F2. Fluorine gas is extremely dangerous. Like, everything burns in the presence of fluorine gas. Even ice burns in the presence of fluorine gas. Not something that you want to mess with. But in the fluorine gas, it's 2 atoms of fluorine that are covalently bonded together. Chlorine gas, you might remember I talked about that one before. This toxic greenish yellow gas. Something else I don't want to be breathing in. Bromine liquid. Remember, there are some nonmetals that are liquids or solids. 2 bromine atoms come together in the element bromine, and that molecule is in the liquid form at room temperature. And lastly, iodine, I2, that molecule is a solid at room temperature. From now on, if I say that something is reacting with oxygen, or it's reacting with nitrogen or hydrogen, what I mean is a molecule of oxygen, a molecule of nitrogen, a molecule of hydrogen, and the formulas are going to be O2, N2, H2. Okay. I call them my super 7 because there's 7 of these diatomic elements, hydrogen, and look at how he's off to the left, right? But then the remaining 6 elements make the shape of a 7 on the periodic table, which I just think is super cool. So I call my super 7, but there's another mnemonic device out there, Brinkelhoff. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Brinkelhoff. The idea is you can say that and remember which 7 elements are the super 7, the ones that exist in nature as diatomic molecules. So however you want to remember it, you need to know those. And of course, this is an online course, so you can have this on a note card and know that fluorine and chlorine, those are F2 and Cl2, etc. Let's have this be our thing, because this our code for this lecture, because this is really important. So we're going to say that if I say something reacts with oxygen, it's reacting with O2. And if something's reacting with nitrogen, then it's reacting with N2 for its formula. Okay, you got that? My super 7, my diatomic molecules, that's what the question will be based on. They're called hydrogen, nitrogen, oxygen, fluorine, etc. When carbon wants to meet up with other nonmetals and metalloids, he wants to borrow electrons too. Carbon is in group 4A. So we know he already has 4 valence electrons. Remember, if the group number ends with the letter A, then whatever that number is, that's the number of valence electrons. How many electrons does carbon need to still, or how many does he still need to be like neon, his nearest noble gas? Well, other than hydrogen trying to be like helium, everybody else is going to try to have the 8 valence electrons that the noble gases have. So let's subtract. He wants 8. He's starting with 4 because he's in group 4A. How many more does he want? He wants 4 more electrons. Carbon must share electrons to get electrons. If he's with a metal or multiple metal atoms, he'll just take their electrons. But when it comes to covalent compounds, he's going to need to share. He must share electrons to get electrons. In fact, he must share all 4 of his valence electrons so that he can borrow 4 electrons. Then he can feel more stable, at least at those times when all 8 valence electrons are around his nucleus. Remember, it's kind of like a shared custody of children, only here it's shared custody of the electrons, or shared custody of the dog kind of thing. When he's sharing his 4, there will be at least one, no, we'll have to have at least 2 other atoms, anywhere to 2 to 4 other atoms sharing their valence electrons with him. And of course, the other atom or atoms will become more stable as well, thanks to carbon sharing his valence electrons. Important, carbon will never be able to make more than 4 bonds because he has only 4 valence electrons to share. Carbon has only 4 valence electrons. He can only make 4 bonds. Please don't make 5 bonds to carbon. It just doesn't happen. It can't happen. He doesn't have enough electrons to do that. Fluorine, meanwhile, he comes to the party with 7 valence electrons because he's in group 7A. He needs only 1 more electron, and then he'll be like neon, his nearest noble gas. Remember, the noble gases, except for helium, have 8 valence electrons. When fluorine shares one of his valence electrons with another atom, he can sometimes borrow one of theirs. This allows fluorine to have 8 valence electrons when it's his turn to have custody of both of those electrons, the one he's sharing and the one that he's getting to borrow from another atom. Here's an example. We've drawn in 1 dot for the 1 valence electron that hydrogen has. We're showing the symbol for fluorine with 7 dots around him. He's in group 7A. He has 7 valence electrons. So these guys bump into each other and they say, hey, let's share. And so these 2 electrons, one from hydrogen and one from fluorine, are being shared. The final drawing needs to have a solid line between those 2 letters, between the hydrogen and the fluorine. The solid line represents the 2 shared electrons. Then we have these extra dots around the fluorine. Well, that's because he didn't use all 7 of his valence electrons to form that bond. He only used 1, but he does still have those other 6 valence electrons around him. And if I'm doing a certain type of drawing, what we call a Lewis structure, which you guys are going to be doing for your assignment, you leave those dots drawn in to show the remaining valence electrons that are not being shared in bonds. So I have dots around the symbols that are valence electrons. The solid lines are bonds made from 2 shared valence electrons, 1 from each atom. Some valence electrons aren't shared in bonds. We call those non-bonding electrons. These unshared valence electrons, most of the time, they're going to be in a pair. They'll go together as 2 valence electrons hanging out together, known as a lone pair. The non-bonding valence electrons are lone pairs of electrons. And so Batman and Robin, that's a lone pair working out there. And that's another cool lone pair. That's just above and beyond everybody else. The number of covalent bonds an atom will form equals the number of valence electrons the atom still needs to be like its nearest noble gas. Let me say that one more time. The number of covalent bonds an atom will form, how many they want, it equals the number of valence electrons the atom still needs to be like its nearest noble gas. Well, that sounds kind of familiar, doesn't it? When we were doing ionic compounds and we were thinking about what charge the atoms would have, remember how we counted the number of electrons they needed to have 8, like their nearest noble gas, or hydrogen needed 2, or when we worked with the metals, they lost electrons so that they could be like their nearest noble gases. Well, with our nonmetals and metalloids, if they're going to be making covalent bonds with each other, we do the exact same thing. Add it up to 8. Each bond that they form is going to be 1 more valence electron for the atom. So if they want 1 more electron, they'll form 1 bond. If they need 4 more valence electrons like carbon did, they form 4 bonds. Our general rule is you have to share an electron to get an electron. Remember, we said carbon only has 4 valence electrons, so he can never have more than 4 bonds. Hydrogen atoms, they only have 1 valence electron. They only have 1 electron, period. Hydrogen can only form 1 covalent bond. I remember the first semester I taught back at Durham Tech, I taught this course, and it was a late night. I was pulling all-nighters about 3 to 4 nights a week, just trying to get everything together for the class. And when I graded that first test or second test, whenever it was, and I saw 2 bonds to hydrogen, or maybe even 3 bonds to hydrogen, the tears just started rolling. So please don't make me cry. Please don't give hydrogen more than 1 bond. He can't get an extra bond when he doesn't have more than 1 electron to share. Boron atoms. Boron has the atomic number of 1, 2, 3, 4, 5. He's in group 3A. It's boron and then aluminum's underneath him. In group 3A, boron has only 3 valence electrons. Boron can form only how many bonds? If you have to share an electron to get an electron. Boron, he can only form 3 covalent bonds. Now, we don't tease him, because look what's happening. The total number of electrons the boron atoms will be able to feel around them, the shared custody and everything, they're never going to have more than 6 valence electrons, 3 that they had to start with, 3 that they're borrowing from someone else. They won't get an octet. Don't tease them. It's not their fault. That's just the way the periodic table made them. 3 valence electrons. The best they can do is 6 total. They don't get an octet. Same as hydrogen and helium. They don't have octets either. So it's okay to be different. I'm going to pause this recording because it's time for our live session. I'll be back in a little bit. I actually have a bit of a conundrum. Since that new class is starting, I'm going to have to stop the recording. So this is the end of part 1. And when we resume, we'll talk some more about covalent bonding and how many bonds the different elements want to be stable. Thanks for watching. See you in the next video.